Hello students, I am Sachitrakar. Welcome to Cars Physics. We are continuing work power energy, and in just previous lecture we have discussed what is work, means introduction to work and conditions to do work. Of course, we have discussed different points under work, means positive work, negative work, zero work, maximum work, minimum work. Okay, and of course we have discussed in detail work done by a constant force. Okay, so work done by constant force, work done by constant force. If you want to calculate work done by a constant force in graphical method, we have discussed analytical method. Then just consider this graph. This is along x-axis, this is along y-axis. Let force is variation of force is shown along x-axis and variation of displacement. Variation of displacement is shown along x-axis. Variation of magnitude of force is shown along y-axis and displacement variation is shown along x-axis. Let a constant force F is applied on a body so that displacement is up to x. So this is 0. Then work done is equal to Fx cos theta. Let's assume displacement is along the direction of force, means here theta is 0 degree. So work is equal to the product of magnitude of force and magnitude of displacement. See, this length represents magnitude of force, this length represents magnitude of displacement. So x is length, AP is breadth, means work can be calculated by calculating area under force and displacement graph. Suppose force is given 100 Newton. It displaces a body through 5 meter along the direction of force, means theta is 0 degree. Then work is equal to 100 Newton into 5 meter is equal to 500 Newton meter, means 500 joule. Okay, SI unit of work is joule. So this is how to calculate work done by a constant force in graphical way. Clear? So in this lecture we will discuss in brief. Work done by variable force. Work done by variable force means force is not constant in this case. In this case, force is changing. Okay, variable force means force is changing. So let's see it graphically first, so that we have a clear concept how to calculate. Okay, let's represent a graph between force and displacement. Variation of displacement is shown along x-axis and variation of displacement is shown along x-axis and variation of force, means magnitude of force, is shown along y-axis. Okay, here work is done by a variable force. Let this is a force which is varying in magnitude continuously. Let we have got a graph between force and displacement. Between force and displacement we got this graph. Then how can we calculate work done by variable force? By using graphical method. Okay, see, suppose let's consider here magnitude of force is F1 and it displaces the body through a very small displacement, that is dx. Okay, F1 displaces the body through dx. Let this point is A, this point is B, this point is C, this point is D. Then what is work done by force F1? So displacement is dx, force is F1. Again we have assumed displacement is along the direction of force. Then dw means work due to F1 is F1 into dx. F1 dx cos 0, F1 dx. See, F1 is length, dx is breadth, means F1 is represented by AB and dx is represented by AD. Then length is AB and breadth is AD, means this is a strip. Then dw is equal to area of strip A, B, C, D. Area of strip. So F1 is force at any instant and displaces the body through dx. Then area under the graph here, area of the strip. Similarly, we may assume this is a force F2 which displaces again dx. Then work done by F2 is F2 into dx, and similarly we may divide the total area under the graph into a number of elemental strips, and finally let this force is Fn, and again it displaces the body through dx. Then to calculate work done by force Fn, then dw is equal to Fn into dx. And similarly, the total area under this graph can be divided into a number of small strips or elemental strips. Number of elemental strips, each of displacement dx, and variation of force F1, F2, F3, F4 up to Fn. Okay. If work done by force F1 is F1 dx, then work done by force F2 is F2 dx. Work done by force F3 is F3 dx. Then what is total work? Then total work is equal to F1 into dx plus F2 into dx plus F3 into dx up to Fn into dx. Means we can write total work is equal to sum of F dx. Let displacement varies from x1 to x2. The sum of F dx and displacement varies from x1 to x2. Then, if you take sum of F dx, it means total work can be calculated by calculating area under force and displacement graph. See, this strip, area of this strip, area of this strip, area of this strip, and area of total strip means total area under the graph. This is the graphical way. By calculating area under graph, we can calculate work done. Sum means, let's consider displacement is from x1 to x2. Then work can be again taken in this way, calculated in this way, sum or integration, same thing. Sum or integration, same thing. Then limit of displacement varies from x1 to x2. Lower limit is x1, upper limit is x2, and the integration of f dx. So in general, work is equal to f ds, and limit varies from s1 to s2. In general, the work may be along x-axis, or maybe along y-axis, or maybe along z-axis, or the work may be on a plane, or maybe in a space. Okay. So this is general formula of work by analytical method, means by mathematical method. Integration of f dx, limit varies from s1 to s2, but here to remember that here f cannot be taken outside of integration. Here f cannot be taken outside the integration. This is important. Why? Because this force is not constant. This is variable force. If force is variable, it can't be taken outside the integration sign. Okay, this is important. Then we will see how to calculate work by using graphical method and using analytical method. Okay, let's see first graphical method. Let's see how can you calculate work by using graphical method, area under the graph. Suppose variation x means displacement along x-axis and variation of magnitude of force shown along y-axis, and let's assume again direction of displacement is along x-axis, force is also applied along x-axis, means theta is 0 degree. So in this case dw is equal to f into dx. Okay, and total work is equal to sum of f dx or area under the graph. Okay, let the graph is given like this. Graph is given like this. Okay, here magnitude of force is 10 Newton. Here magnitude of force is 20 Newton. And this displacement is 0 to 2 meter, and here 0 to 4 meter, and here from 0 to 6 meter. Then it is asked to calculate work done, total work done. Okay, see, first force increases from 0 to 10 Newton, so this force is variable force. Okay, but this force means the force which displaces the body from 2 meter to 4 meter is constant. This is constant force, means 10 Newton. Thereafter, for displacement 4 meter to 6 meter, force is increasing from 10 Newton to 20 Newton. So this is variable, this is variable, this is constant. Okay. So simultaneously we can calculate total work, means work done by variable forces and work done by constant force, and we have discussed how to calculate work done by constant force by using graphical method, area under the graph. Here also work done by variable force can be calculated, calculating area under the graph. Okay, then let this area is A1, this area is A2, this area is A3. Then total work is equal to total area under the graph, means A1 plus A2 plus A3. Is it clear? Then A1. A1 is area of this triangle. Base of the triangle is 0 to 2, means 2 meter, and perpendicular is 0 to 10 Newton, means 10. Then area is A1 half base is 2 meter, and perpendicular is 10 Newton. This is A1 plus A2. A2 means area of this rectangle. Okay. Length is 2 meter to 4 meter, means 2 meter, and this is breadth is 10 Newton, means 2 meter into 10 Newton, plus area A3. To calculate this area in easiest way, divide the area into two parts. Total area is 8. So this height, this perpendicular is 10 Newton, means from 10 Newton to 20 Newton is 10 Newton, and this base from 4 meter to 6 meter means 2 meter. Then total area, this total area of triangle plus area of rectangle. Area of triangle half, base is 2, height is 10, plus area of rectangle. Base is 4 meter to 2 meter, sorry 6 meter is 2 and height is 10 Newton. 2 into 10. Now calculate total work. 2 to 10 plus 20 plus 2 cancels, 10 plus 20, 30. Then this comes 60 Newton into meter means joule. This is the way to calculate graphical method. Calculate work by using graphical method by calculating total area under the graph. Okay. Next, some simple numericals. Work done by variable force. Is it clear to you? Is it clear to all? Okay. A force F is equal to 10x I cap. 10x I cap means force is acting along x-axis. I cap shows direction of force. Direction of force is along x-axis. Okay. Displaces a body from x1 is equal to 1 meter to x2 is equal to 2 meter. Very simple question. Means force is applied along x-axis and displacement is also along x-axis. So angle is 0 degree. Angle between force and displacement is 0 degree. Then what is dw in this case? Motion is along x-axis. dw is equal to f dx cos 0 degree means f dx. To get total work, integrate both sides. Total work is w. Integration of f, magnitude of force is 10x into dx, and distance means displacement varies from 1 meter to 2 meter. Easiest. Then this is bring 10 outside. Integration of x dx means x to the power 1 into dx, x to the power 2 divided by 2, x to the power n plus 1 by n plus 1, and limit varies from 1 meter to 2 meter. Then work is equal to 10 by 2 is 5. X square, put first upper limit 2 square, then lower limit 1 square. Then work is equal to 5 into 4 minus 3. Sorry, 4 minus 1. 4 minus 1 is 3. 3 into 5 is 15. 15 joule. The simplest one. Is it clear? Fine. Is it clear? Okay. The next question. Just go on observing the questions, then clarity will come. Okay. Next question, a force up or a force F is equal to. Again variable force. See, in previous question we have discussed force applied along x-axis I cap. Let's consider now force is acting on a plane, force is applied on a plane, on a body. Okay. So motion on a plane, directly speaking, motion on a plane. So x force is given as x I cap plus 2y square j cap. X-axis, y-axis. Force is acting on the plane and motion of the body is on the plane. Okay. Displaces a body. Displaces a body from one position to another position. Displaces the body from one position to another position left. Displaces from 1 meter, 2 meter to 4 meter, 3 meter, and I am taking one negative value minus 1 meter. Okay. So this position is the initial position, means here x1 is equal to 1 meter, y1 is equal to 2 meter, for this x2 is equal to 3 meter, y2 is equal to minus 1 meter. Then what is work? then total work is equal to, how can you calculate total work? I will go to first method, then I will return to this numerical. First see the method. See. Take Cartesian coordinate system. This is x-axis, this is y-axis, on this plane, parallel to this plane, and this is z-axis. This is origin, coordinates are 0, 0, 0. Let initially particle is at P, coordinates are x1, y1, z1, and position vector of initial position of the particle is r1. Now a force is applied. I am showing what is expression of applied force. Applied force is equal to Fx I cap plus Fy j cap plus Fz k cap. Means the particle is moving in space. Particle is moving in space. X, Y, Z coordinates are given. We may use coordinates for plane. Suppose Z, along Z axis motion is not given, then we are considering XY plane, or XZ plane, or YZ plane. Okay. So, force is acting on the particle and the particle is displaced to a new position Q. Coordinates of Q are x2, y2, z2, and position vector of point Q is r2. So, PQ is a displacement. Let's take it dr. Okay. dr, the expression of dr is very easy. Usual form, position vector is this position vector x1 I cap plus y1 j cap plus z1 k cap, this position vector x2 I cap plus y2 j cap plus z2 k cap, but in general, position vector is x I cap plus y j cap plus z k cap. Accordingly, here x1, y1, z1, and here x2, y2, z2. Then what is dr? What is dr? If in left side we are using dr, derivative of r, then right side we will take derivative. Means in place of x we will write dx I cap. In place of y we will write dy into z cap. In place of z, dz. This is expression for displacement, or you may think like this. R1 is equal to x1 I cap plus y1 j cap plus z1 k cap. Similarly, R2 is equal to x2 I cap plus y2 j cap plus z2 k cap. And considering the triangle OPQ, considering triangle OPQ, you see OP and PQ are in same order, means clockwise order, and OQ in anti-clockwise order. Just apply triangle law. Just apply triangle law. OP vector plus PQ vector is equal to OQ vector. Then OP vector is R1, PQ vector is displacement dr, and OQ vector is R. Then dr means displacement vector is R2 minus R1. I am writing here dr. R2 minus R1, x2 I cap minus x1 I cap. In simplest way we do it, x2 I cap minus x1 I cap. Bring I cap common, then x2 minus x1. Similarly, y2 j cap minus y1 j cap plus y2 minus y1 into j cap. Similarly, z2 k cap minus z1 k cap, z2 minus z1 k cap. And again, you may write like this: x2 minus x1 means change in displacement in x-axis, x2 minus x1 dx I cap, y2 minus y1 dy j cap, z2 minus z1 dz k cap. Same thing. This is easiest to, you may follow this. Right. Can I erase this now? Very good. This is expression for dr, and this is this is expression for force, and dw is equal to f dot dr. Then dw is equal to f fx I cap plus fy j cap plus fz. dot dot. In place of df, we can write dx I cap plus dy j cap plus dz I cap dot I cap 1, j cap dot j cap 1, k cap dot k cap 1, simply dot product in terms of rectangular components. So dw is equal to fx I cap dot dx I cap fx dx, fy j cap dot dy j cap fy dy, fz k cap dot dz k cap fz. Then to get total work, integrate both sides. And here I am writing the final expression. Total work W is equal to integration of fx dx plus integration of fy dy plus integration of fz dz. If you want to put limit, then variation of displacement along x-axis, let from x1 to x2. Along x-axis, displacement is from x1 to x2. Similarly, in y-axis, displacement is from y1 to y2. In z-axis, displacement is from z1 to z2. This expression, you should keep it in your mind. We'll use this now itself. Okay. Then come to the question. Expression for force is given and positions, two positions, body is displaced from this position to this position, and accordingly position vectors are x1 I cap plus y1 j cap, and here position vector is x2 I cap plus y2 j cap. Okay. Then we will use this formula in very simpler way. To get the answer, we have to find displaces a body and given you the output of coordinates, calculate work. Then use this formula. Work is equal to x1 to x2 fx dx plus y1 to y2 fy. Here z coordinate is not given, so we will use xy only. Then x1 is 1 meter, x2 is 2 meter, fx. In place of fx I cap, fx is x into dx plus integration of y1 to y2, x2 is 3, x1 is 1 meter, x2 is 3 meter, 1 meter to 3 meter plus y1 is 2 meter and y2 is minus 1 meter. Then fy, magnitude of fy is 2y square into dy. Then just integrate to get our result. Integration of x dx is x square by 2. Limit varies from 1 meter to 3 meter plus 2y square, bring 2 outside. Then y square dy. Integration is y to the power 2 plus 1 y cube divided by 2 plus 1, 3. Limit varies from 2 to minus 1. Now, total work is equal to 1 by 2. 1 by 2, bring it outside. X square means upper limit 3 square minus lower limit 1 square plus 2 divided by 3, 2 by 3. Y cube means upper limit is minus 1 cube plus lower limit is 2 means 2 cube. Just calculate it. Work is equal to half. 3 square is 9 minus 1 plus 2 by 3 minus 1 cube minus 1 into minus 1 plus 1 into minus 1 plus 1. Minus 1. Minus into minus minus 1 plus 2 cube means 8. 9, 1 minus 1, 8. Then work is equal to 1 by 2 into 8 plus 2 by 3. 8 minus 1 is 7. Then work is equal to 4 plus 14 by 3. Just calculate. This is 3. LCM is 3. 3 into 4, 12 plus 14. 26 by 3. Then check your calculation. Check your calculation. X square by 2. Y cube by 3. 1, 2, 3. 2, 2 minus 1. 1 by 2. 3 square minus 1 square. 2 by 3. Minus 1 cube. Sorry. This is minus 2. This is minus 2. This is minus. Then it is minus 9. Okay. And finally it will come. This is minus 18 by 3. A minus. This is minus 1, minus 8, minus 9. Minus 9 into 2, minus 18. So work is equal to 4. Minus 6 is equal to minus 2 joule. Okay. This is minus. Okay. This is also minus. So minus 2 joule. Okay. Next question. Next question again, we will take on a plane, let a force F is any value on XY plane, on YZ plane or ZX plane, any value you may take. So a force of 10 xi cap plus 4 yj cap means again xy plane. 10 xi cap plus 4 yj cap. This force is variable since x and y coordinates go on changing, force will also go on changing. This places a body from a point P of position vector R1 means initial position is P and position vector of point P is R1. You may take any value 3i cap plus 8 j cap to a point, to a position, to a point Q of position vector R2. So Q is another position, Q is a new position, so R2 vector. Let's take R2 is equal to 5i cap plus 4. 5i cap plus 4. You may take negative also. Take this minus 5i cap minus 4j cap. Okay. Then what is work done? Simple question. What is work done? Then dr is equal to R2 minus R1. As we have discussed. In Cartesian coordinate system, we have discussed now itself. Dr is equal to R2 minus R1. Is it clear? Then R2 is equal to 5i cap minus 4j cap minus R1 3i cap plus 8. Then dr is equal to 5i cap minus 3j cap. 2i cap. Sorry, 5i cap minus 3i cap is 2i cap minus 4j cap minus 8j cap minus 4j cap minus 8j cap means minus 12j cap. This is dr. Then we have to calculate work. See, work is equal to integration of f dx. Limit varies from x1 to x2. Fx dx, fy dy, limit varies from y1 to y2. You may take directly dot product, where here x is variable, we can't take directly dot product. So this is not required. I'll write in this form x1, see, x1 is 3, expression of R1, x1 I cap plus y1 j cap. Expression for R2 x2 y cap plus y2 j cap. Then what is x1? x1 is 3. x1 is 3. And what is x2? x2 is 5. x1 to x2. fx. Magnitude of fx is fx I cap 10x. Magnitude of fx is 10x into x plus integration of fy dy. But limit is from y1 to y2. So what is y1? y1 is 8. y1 is 8 and y2 is minus 4. y2 is minus 4. Minus 4. And fy is 4y. Magnitude of fy is 4y into dy. Now calculate work is equal to 10. Bring 10 outside. X dx. Integration is x square by 2. Limit is from 3 to 5. 3 to 5. Plus. Bring 4 outside. Integration of y dy. Y square by 2. The limit is from 8 to minus 4. 8 to minus 4. Okay. Now I may calculate in easiest way. 10 by 2 is 5. 10 by 2 is 5, then x square, put first upper limit 5 square, minus lower limit 3 square, plus 4 by 2 is 2, y square means minus 4 square, minus lower limit 8 square, minus 4 square minus 8 square, then work is equal to 5 into 25 minus 9, 5 square 25, 3 square 9, plus 2 into minus 4 square is 16, minus 8 square is 64. Then work is equal to 5 into 16. 25 minus 9 is 16. 2 into minus 48. 64 minus 16 is 48. Then work is equal to 16 into 5, 80. This is minus 48 into 2. 96. Then it's minus 16. Minus 48 into 2 minus 96. 16 into 5 is 80. 96 minus 80, 16, but negative. Negative work is 16. Is it clear? Is it clear? Okay. The next question. Again a force. I am not erasing a force. I am not erasing a force F. Again, a force F is equal to xi cap plus 3y. Xi cap plus 3y j cap, again the force is on the plane of xy. Displaces a body. Displaces from point P. I am not writing complete question. From point P, coordinates of point P are 2 meter, 3 meter, 2 Q. Coordinates of point Q, you may take any value as we select 3 meter, minus 1. Then we have to calculate work done. This force displaces a body from this point to this point. So this is x1, this is y1, this is x2, this is y2. Then total work is equal to integration of fx dx, x1 to x2, plus integration of fy dy, y1 to y2. Then work is equal to fx, magnitude of fx is x dx. Then x1 is 2 meter. x2 is 3 meter plus integration y1 to y2, y1 is 3 meter, y2 is minus 1 meter. 2 meter to 3 meter, 3 meter to minus 1 meter, then magnitude of fy is 3y, 3y. Then just integrate and get your answer. Work is equal to x square by 2, limit is from 2 to 3. Plus 3y dy, 3, bring it outside, y square by 2, limit is from 3 to minus 1, now you can calculate it. Okay. Now we can calculate it. Okay. Then another beautiful example of variable work done by variable force. See, suppose a spring is attached. A spring is attached to a fixed support. This length is original length of spring. Original length of spring. Okay. In second diagram, I am showing you now a force is applied. This end is fixed. A force is applied so as to elongate the spring. Now, a force is applied to elongate the spring. The spring is elongated to some extent. And force applied is external force or deforming force, we may say it F external. So up to this is original length and this is elongation. Elongation. Up to this, that elongation is x. Elongation is x, but think, if now this force is removed, this force is released, we are pulling the spring and this is elongation produced. Now if this force, external force is removed, then the spring will come back. The spring will come back to its original configuration, means original length. Why? Deforming force or external force elongate the spring. If the force is removed, then it will come back to its original configuration. Why? Because while elongating the spring, a force acts in the spring. This force is called as spring force or restoring force or elastic force. This is the deforming force or external force which deforms, elongates the spring, and spring force acts opposite to the direction of external force. See, elongation is in this direction, but force is acting in opposite direction. So if this force is removed, then this restoring force will bring back the spring to original configuration. Means in this case, this force means restoring force proportional to negative of elongation, which because they are in opposite direction. They are in opposite direction. So force is equal to a constant into minus x. This constant is called as spring constant or spring factor or Stephan's constant. Stephan's constant. So, very important to know, spring constant is inversely proportional to length of the spring. Spring constant is inversely proportional to length of spring. Means, if you consider, this is a spring. Total length is L. If the spring is cut into two equal parts, then what will happen to spring constant of each part? Spring constant inversely proportional to length. If length is halved, then spring constant will become double. If spring constant of total spring is K, and if it is cut into two equal parts, then spring constant of each half of the spring will be 2K. Similarly, if a spring is cut into n number of n equal parts, then spring constant of each part is nk. Suppose the spring has spring constant k, it is cut into 10 equal parts, then spring constant of each part will be 10k. Okay. If length decreases, spring constant increases in accordance with this relation. Is it clear? Okay. Then this is about restoring force. Then work done. See, deforming force is doing positive work because force and elongation are in same direction, but spring force and elongation are in opposite direction, so spring force does negative work. So dW is equal to spring force dot displacement. Since elongation and force are in opposite direction, so dW is equal to ftx cos 180 degrees, so dW is equal to minus ftx. So dW is equal to, in place of f, I can write minus kx into dx. So dW is equal to kx dx. No need to take negative because work is scalar quantity, just we want to know magnitude of total work. Magnitude of work. Negative sign shows that the work is negative. Okay. Then integration of dW. Integration of kx dx 0 to w. Let the spring is elongated from 0 to x. Then work done is w, k is constant, bring outside. Then integration is x square by 2, limit from 0 to x. Then work is equal to half k into x square minus 0, means work is equal to half k x square. Okay. But if the spring is elongated from x1 is equal to x to x2 is equal to, or from x1 to x2. If the spring is elongated from x1 to x2, then what will happen? Only you have to change the limit. Integration of dw is equal to integration of kx dx. Limit varies from initial to final, x1 to x2. Then work done is w, k is constant, bring it outside, x square by 2. Then work is equal to half k, limit is from x1 to x2, half k, in place of x put upper limit x2 square minus x1 square. In this way you can calculate work done in elongating a spring. This is also potential energy stored in a spring. This is also potential energy. Means if the force is removed, then energy is already stored in the spring, due to which it will again come back to original configuration and numericals will be on direct level. Okay. The C1, a spring of spring constant 100 Newton per meter, force by length Newton per meter, elongates is elongated through 10 centimeter. Then what is work? What is work? In elongating the spring, what is work? Okay. In elongating the spring, then work is equal to half k into x2 square minus x1 square. So work is equal to half, k is 100, x2 square is 10 centimeter, means 0.1 square, and x1 is equal to 0 in this case because it is elongated through 10 centimeter, means from 0 to 10 centimeter. 10 centimeter is 0.1 meter, 0.1 square, then work is equal to 100 by 2 is 50, 0.1 square means 1 by 10 square, 1 by 100, so work is equal to 1 by 10 square, 1 by 100, so 50 by 100, 1 by 2 or 0.5 joule. Simpler questions, okay. Then finally we'll go to unit system of work. This is also important. Unit system of work. Units of work. Units of work is divided into two types. First one, absolute unit. Next, gravitational unit. So, formula for work is equal to Fs. We are considering displacement is along the direction of force, means here theta is 0 degree. Force and displacement are in same direction. Of course, unit doesn't depend upon cos theta, but here we have considered theta is 0 degree. First bit, absolute unit, first bit, mks. So work is equal to Fs. Here F is equal to 1 Newton. In mks, absolute unit of force is 1 Newton and displacement is in mks 1 meter. Theta is 0 degree. So work is equal to 1 Newton into 1 meter. That's equals to 1 joule. But if one asks you to define 1 joule, very simple form. See, work is 1 joule or work done is said to be 1 joule if 1 Newton force of 1 Newton displaces a body through 1 meter along the direction of force. Theta is 0 degree. Work done is said to be 1 joule if a force of 1 Newton displaces a body through 1 meter along the direction of force. Means force and displacement are in same direction. So theta is 0 degree, cos 0 is 1, work is equal to Fx. Is it clear? Then in CGS. Here, unit of force is a dyne, 1 dyne, and unit of displacement is 1 centimeter. Then work is equal to 1 dyne into 1 centimeter, and you know it, this is 1 arc. And 1 joule is equal to 1 Newton into 1 meter. And 1 joule, 1 Newton you know, 10 to the power 5 dyne, and 1 meter is 10 to the power 2 centimeters. So 1 joule is equal to 10 to the power 7 dyne into centimeter is arc. And finally, this may not be required for you in FPS system. In FPS system, here force is 1 pounder, displacement is 1 foot. So work is equal to force into displacement 1 pounder into 1 foot. It is called as 1 foot pounder. May not be required for it. Then gravitational unit. First bit, MKs. Here, force, unit of force is 1 kg weight or 1 kg force. And displacement is again, in MKs it is meter, displacement is in meter. Then work is equal to Fs cos 0 is 1 kg weight into 1 meter. This is called as 1 kg meter. Gravitational unit of work in MKS is 1 kg meter. Then conversion 1 kg meter. Very important. It is required always 1 kg meter. You see, 1 kg meter is equal to 1 kg weight into 1 meter. 1 kg meter is equal to 1 kg weight into 1 meter. But 1 kg weight is 9.8 Newton into 1 meter. So 1 kg weight is 9.8 Newton into meter is joule. So 1 kg meter is 9.8 joule. Means the simpler way to convert gravitational unit to absolute unit. Absolute unit is joule. To convert gravitational unit kg meter to absolute unit, just multiply the value of acceleration due to gravity. In m case, value of acceleration due to gravity is 9.8. So 1 kg meter is equal to 9.8 joule. In series, here force is equal to 1 gram weight or 1 gram force and displacement is 1 centimeter. Then work is equal to 1 gram weight into 1 centimeter. It is written as 1 gram centimeter. Here 1 kg meter, here 1 gram centimeter. And in this way, we may solve it. 1 gram centimeter is equal to 1 gram centimeter is equal to 1 gram weight into 1 centimeter. 1 gram weight is equal to 980 dyne into 1 centimeter. Then 1 gram centimeter is 980. 980 dyne centimeter is arc, so 1 gram centimeter is 9.8 arc, 980 arc means value of acceleration due to gravity 980 is multiplied. Okay, just convert gravitational unit to absolute unit. Just multiply value of acceleration due to gravity and finally you know it. Dimensional formula of work. Dimensional formula of force m1, l1, t to the power minus 2, displacement is length l to the power 1, and solving it you will get m1, l2, t to the power minus 2. Okay. So this is the end of this lecture, lecture 2. In next lecture, again, I will meet you with a beautiful concept of work. Thanks, my children. Thanks.